In this final video for Chapter 18, I'd like for us to take a look at some actual chemistry that involves conjugate addition and nucleophilic aromatic substitution. And we're going to be looking specifically at the synthesis of this antibiotic that's called levofloxacin. Levofloxacin is an antimicrobial agent, and it works through the inhibition of bacterial DNA synthesis, specifically through the action on the DNA gyrase enzyme. And the DNA gyrase enzyme is an enzyme that's involved in DNA winding and unwinding. So essentially what this drug does is it blocks DNA cell replication. It is active against several different bacterial infections, most notably urinary tract infections, respiratory tract infections, including pneumonia, which is kind of a big deal right now. And fairly minor skin infections. It is on the list of WHO essential medicines, but this antibiotic is known to have serious side effects, and recently in the United States it's kind of been sidelined as a result. And so it's used in the United States anyway. It's used as kind of one of those antibiotics that people take when other antibiotics are not an option. The synthesis that is shown here is the industrial synthesis, and I'm going to take you through a couple steps of this synthesis and really try to highlight the conjugate addition and nucleophilic aromatic substitution steps. So we're starting off with this acid chloride, and we can accomplish this Claisen condensation followed by a decarboxylation when we treat this dicarbonyl with a base. The nucleophilic carbon will add to the carbonyl carbon, effect a substitution, and then we would lose this part of the molecule through decarboxylation. Again, we're not going to go over the mechanism, but it might be to your benefit to try out these mechanisms to see how far you can get. See if you can account for the formation of this product, knowing the reactions that go into this step. All right, the second step of this synthesis is going to be creation of this vinyl ether here, right? So we're treating with triethyl orthoformate and acetic anhydride. This is going to be a funny mechanism. Where the acetic anhydride activates the triethyl orthoformate while also creating a base that can deprotonate this carbon. If you want to try out this mechanism, I recommend it. If you have any problems, please contact me and we can go over this mechanism more specifically. What I really want to get into is looking at these last few steps that involve first a conjugate substitution, and then a series of nucleophilic aromatic substitution steps. So here we see that we're creating an alpha beta unsaturated carbonyl, and this double bond here is actually conjugated to two carbonyl compounds. We're adding this amino alcohol, which is actually just a reduced form of alanine, the amino acid, and so we're dipping into the chiral pool in order to make this chiral compound. And again, this is made through reduction. We're not going to go over the specific conditions that allow for this reduction, but you can imagine that we can reduce this carboxylic acid carbonyl down to an alcohol. When that happens, now we have an amine that can add in a 1,2 sense to this beta carbon, push the electrons up to one of these two carbonyls, and then when they fall back down, we would kick out that ethoxide. Again, this is not a direct substitution, right? So this would happen through two steps. First, an addition, formation of an enolate intermediate, followed by an elimination, which would kick out the ethoxide. And you can see that we're replacing this ethoxy group with this amino group. So this is the conjugate addition step, right? The 1,4 addition followed by an elimination. The next series of steps are all going to be nucleophilic aromatic substitution. And I think it's important to point out that even though nucleophilic aromatic substitution is something that we go over in class and something that we study theoretically, it is a reaction that is heavily used in the synthesis of aromatic pharmaceutical compounds. So let's take a close look at what's happening here. Right, so you can see on this arene ring we have 4 fluorines, and when we get to the product, right, only one of those fluorines remain. And so this arene group is going to undergo 3 sequential nucleophilic aromatic substitutions. If we take a look at these fluorines, you can see, or if we take a look at this ring, you can see that there is one mesomeric electron withdrawing group in this carbonyl, and that should activate this position here that is ortho to the electron withdrawing group, and this position here that is para to the electron withdrawing group. In addition, we will also be losing this fluorine, which we'll go over how that occurs, despite the fact that this fluorine does not have an ortho or an electron withdrawing group that with an ortho-para relationship. So whenever we treat this compound with sodium hydride is a base that we can think of as a kind of an ionic base, where we have a positively charged sodium ion and a negatively charged hydride or hydrogen anion. This is a very good base, and we actually consider this a hard base. Right, so this cannot act as a nucleophile, right? So we learn that whenever we want to add hydride as a nucleophile, it has to come in the form of copper hydride, sodium borohydride, or lithium aluminum hydride. Sodium hydride is not nucleophilic. Right, and is actually really only going to act as a base. And in this case, the proton that it's going to pull, and there are several protons that it could pull, but the proton that it's going to pull is the proton on this nitrogen. When it does that, we're going to form an anion on that nitrogen, which can then add into this carbon. Right? This is going to be one of the most active sites for nucleophilic aromatic substitution because of the ortho electron withdrawing group that can stabilize the anionic intermediate. And we'll be able to make a 6-membered ring by closing this nitrogen onto this carbon and kicking out the fluoride. You can see there are a couple of conditions that are shown here, right? The first is going to be sodium hydride in DMSO. The second is going to be potassium hydroxide in water. So once we close this 6-membered ring by attaching this nitrogen to the carbon, that's going to bring this oxygen group into close proximity with this other carbon. You might be looking at this and saying, well, this fluorine or this position on the ring that has the fluorine does not have an ortho or para electron withdrawing group. However, there is going to be an ortho fluoride, which should be able to stabilize that anion enough to allow a second nucleophilic aromatic substitution to occur. So once we add the amine to this carbon and effect a substitution, the second set of conditions, basic conditions, potassium hydroxide will be able to deprotonate this oxygen, and the oxygen can add into this carbon here. The anion will be stabilized by the orthofluoride, and then it will be able to affect the elimination and kick out this fluoride. And so you can see in this compound, we've made these 2 bonds both through nucleophilic aromatic substitution, and we've made this bond here through 1,4 addition followed by elimination. And in the starting or in the final product, these are the 3 bonds that we've made through conjugate addition or nucleophilic aromatic substitution. The last step of the synthesis is going to be the addition of this dinitrogen compound, this cyclic dinitrogen compound, to this carbon, which, if you think about it, right, there are 2 available positions for nucleophilic aromatic substitution. Only this position has an electron withdrawing group that will help to stabilize the anionic intermediate. Here, the electron withdrawing group has a meta relationship, and then in the position which undergoes substitution, the electron withdrawing group has a para relationship. So that amine can add to this carbon. Pyridine is in there as a base to deprotonate that nitrogen, and whenever this undergoes nucleophilic aromatic substitution, we're making the target compound levofloxacin, right? And so in this bond here, you can see all three of these are going to be formed through nucleophilic aromatic substitution, whereas this is going to be formed through conjugate substitution. All right, so you can see that this chemistry that we're studying actually has real-world application to the synthesis of organic compounds. A lot of the reactions that we've studied this year are meant more to illustrate the reactivity of intermediates or the reactivity of functional groups, but are not actually carried out in a lab or have evolved into much more specialized reactions that are carried out in the lab. Nucleophilic aromatic substitution has not evolved too much over the years and is used extensively in pharmaceutical synthesis just because there are a lot of pharmaceuticals with that have aromatic functionality in them. This is going to be the final video for Chapter 18, and hopefully you were able to learn a lot about conjugate addition and nucleophilic aromatic substitution.